Okay. Thank you. Good morning or good afternoon, everyone. Good evening, everyone. This is Zong-Liang from UT Austin in the US. Thank you, Paul Smith, for inviting me to give this talk. This is a work between UT Austin and the City of Austin. We are trying to provide climate information in their water planning for the City of Austin. For those of you who have been to Austin, Texas, or for those of you who have not, Austin is the capital of the state of Texas. It's a rapid developing city with a population in the metropolitan area over more than 2.4 million people. It's a high-tech hub. If you know, San Francisco is a Silicon Valley area. This Austin is called Silicon Hill because hill country, lots of rolling hills. In the past, we have very severe droughts, also subject to heavy flooding, and in the future warming climate, the big concern whether we have enough water to supply the growing population. Can you move on to next slide? So this leads to the project we collaborate with City of Austin in the so-called Austin Water Forward 2024. Basically, every 5 years, the city is required to produce updated water planning for the future from current to 21-20. This 100-year plan includes addressing the water availability, addressing all kinds of uncertainties in climate, in population, and supply-demand sectors. The second figure, in the middle figure, you see Water Forward 2024. This report actually was published in November last year, just 1 year ago, after a few years' work. Thank you. And move on to next one. Can you move on? So when we work with them, we need to determine future climate. And to get credible information for future climate, we need to know how those models are performing and modeling the current climate. So how to choose climate models for urban water planning. This has been a central focus in the beginning project. We will benefit from this article published by John Nielsen Gaiman in Earth Future. As you can see from this article, which has many authors, some are involved in this project. Can you click to see the animation? In the recommendation from this paper is it really promotes applications of GCMs or Earth system models to provide information for stakeholders in adaptive planning. Really envision co-production involving engaging both stakeholders and the climate scientists to work together to understand each other's needs. But challenges, as I just mentioned earlier, there's a gap between available from model and needed information. Previous speaker already touched on this, and also how to address reliability of the models in make decision. Can you click to see? So that one way to address this is we really need to have a comprehensive evaluation of the models before we use them for providing climate information for the future. Okay, move to next slide. Click. So this is a team involving UT Austin and the City of Austin. From UT, we have 3 professors, me, Paula Pasalacqua, who recently also, I think after the conclusion of this project, she's now in ETH in Switzerland now, and Gita Prasad and Dev Nelgi, actually 4 professors, and 1 postdoc and 1 student. And the City of Austin, the manager is Maria Flores Gonzalez and Helen and Sarah And also we have Richard representing the private consulting firm. Move on to next slide. So the key issue here is how to pick up the best performing GCMs for this Colorado River Basin, and because Colorado River Basin is a river basin which supplies surface water needed by city of Austin and also downstream regions. We know GCMs doing well on global circulation patterns, but for local scale hydrology, how do they perform? And whether they can provide needed information to address water resources. This is the main question we need to address. Can we move on to next slide, please? Here for you can see here the Colorado River Basin, showing a highlight within the state of Texas, which is one of the major river basins flowing to the Gulf of America or Gulf of Mexico. For the top panel, you see spatial patterns of precipitation, temperature, and dry days. Basically, number of days which each day the daily rainfall less than 0.01 inch. We consider it's a dry day. All of those three variables are critical for managing droughts and water resources. The bottom panel showing the seasonality of precipitation, temperature, and dry days. Those are based on observations such as the PRISM data sets. So move on to next slide. So for those spatial patterns and seasonality, we evaluate all the 35 GCMs or ESMs from CMIP 6 and using the well-known Taylor diagram to compare all of them. As we have 35 models, you can see for the spatial patterns, they are all the models are performing much better than what you will see in seasonality because they are closer to observations, more or less. And next slide, showing the seasonality or temporal pattern, you can see the temporal performance is generally as we expect. Seasonality rainfall, the timing rainfall over the year is relatively weak from all of the models. So move on to next slide. We need to rank all the 35 GCMs based on the three variables: precipitation, temperature, and the number of dry days. We introduce overall skill score in addressing all of those three variables, also their spatial patterns as well as temporal patterns, because spatial patterns are much better simulated. We give them more weight. You can see the 2 here in the formula in the bottom of the diagram, the figure here, slide here, and we put 1 in the front of seasonality. So this is an overall skill score to evaluate all the GCMs and for the three variables. Can you move on to next slide? What you see here is for the top 10 ranked ESMs for the in terms of their skill of performance for the Colorado River Basin. The one highlighted in yellow are the 5 GCMs we selected based on not only based on their performance, but also based on their relative independence and output availability. But overall, you can see the individual ranking for spatial temperature, spatial precipitation, and spatial number of dry days, as well as the seasonality for those three variables, and overall ranking, and overall skill score, overall ranking. If you move on to next slide, you will see the specific considerations we put in selecting those 5 GCMs. Overall, because we are charged to produce these results within first 12 months. So based on economic and time consideration, we only select 5 best GCMs and pick 3 scenarios. Can we move on to click the button? Those are the 5 GCMs based on the availability of outputs. Also, you can see here for each of those GCMs, their composition of atmosphere model, ocean model, land model. You see there are some similarities, also differences. And this, based on their performance and their relatively independence and the data availability, we believe this represents a reasonable set of models. And move to next slide. So here is the 5 GCMs, and we pick 3 scenarios from SSP 1 2.6, SSP 2 4.5, and SSP 5 8.5. And the 5 GCM 3 scenarios, and this is basin-wide average temperature over the historical period, and also extending all the way to the end of this century. You can see the overall trajectory of temperature change and the temperature spread given different scenarios, different models. We also have done that for the precipitation and the other variables. Okay, move on to next slide. We also have done the bias correction for temperature, precipitation, number of days using quantile to quantile mapping, or other types of bias corrections. Details described in this article by July 2025. The detailed reference will be provided at the end of the presentation. So to derive runoff, we decided not to use the model runoff because model runoff strongly depends on surface hydrology from the GCMs. And therefore, we are using this machine learning based framework to calculate stream flow. And to calculate stream flow, we identify the weather features, up to 25 different weather features, like daily precipitation, temperature, and number of days without rainfall, so on and so forth, for more than 25 features. And with 45 control points that provides detailed stream flow measurements. So we developed this framework, machine learning framework, neural network based to relate from a coarse grid weather data sets to the gauge-based stream flow. Details are provided in the paper showing here. And move on to next slide. This is the actual the details list of the 25 weather features, and that's on the left-hand side. Right-hand side is the derived stream flow for the future based on 5 models. You can see on the right-hand side, top left is from XS model, and the top right SIGN RM model. Then we have in the middle EC, Earth-3, and KEC, and the bottom UK ESM. The 5 GCMs, and over with 3 scenarios, you can see the overall at the end of the century, the models, all models point to a drier or reduced naturalized stream flow compared to the black line, which is the historical mean. So this information is very important as input for the water availability model, which is the calibrated model for managing water resources in the state of Texas for different river basins. And move on to next slide. So that can calculate how the monthly flow in terms of acre feet, which is a volume unit, for the based on a WAM model, and also based on GCM historical, and from the 3 future scenarios. You can see for the for the immediate future from 2021, 2040, and mid-century from 2041, 2060, and near end of century 2061, 2080, and also the end of century 2081, 2100. So you can see the different scenarios and different periods and different the overall the ensemble models. The bottom line is projected decline of stream flow by 2100. Also, you can see the variance indicating variability in extreme events. Next slide. To use this information to provide this information for water planning for state of Austin require additional considerations, as you can see from this table. From climate future, that we can further generate hydrological scenarios based on the droughts comparison of the historical drought record, such as the 2010 drought, a severe drought in Texas, and also the ocean water demand scenarios like high, low, and baseline demand, as well as regional supply scenarios from different off-channel aquifer storage and recharge and brackish water retreatments and reuse, those considerations. So there are 666 scenarios which are further produced, and the stochastic modeling is generated addressing those scenarios, and the results will be used for informing water decision. Moving to next slide. So here I want to provide a central message. Why do we add stochastic modeling or resampling after the careful GCM selection? Bottom line is we are not throwing away the effort to select GCMs. We are using the 5 skillful GCMs to give us correct climate change forced shift for this river basin, but we use stochastic method to explore a range of plausible multi-year drought scenarios sequences around this projected new climate that could impact water supply planning with plausible extremes. And next slide is a further consideration, because you need to have a large enough ensemble to provide information for making water planning decisions to really address the short, from CMIP models and from available outputs. Those are still relatively a small sample. So we have to use this approach to generate a large enough sample for water planning purpose. I do not want to read the detailed list here. Let's move on to the take-home message. Okay, keep this, move on to the later on. Next. So this take-home message is, so first of all, we work closely with City of Austin we have bi-weekly meetings in carrying out this project. So we have made careful effort in selecting GCMs and then designing a framework and to generate stochastic modeling and other scenarios to provide information for water planning. And that eventually leads to the published reports. And also when releasing the reports to the public, there was open session to address all questions from users and the public. So here I have a general call to action. CMIP is wonderful. As we know, the CMIP 7 is going to be available, and we like to continue work with CMIP community when this new data set is available. And for this project to engage with the city, local water authorities, I think more effort really needed to talk to each other, engaging both CMIP community and also local water planning community. Next slide. This is references for the paper, July, that's already published this year in AWA Water Science and the Nielsen Gammon paper. And also this work was interviewed by editor from Science. You can see his future. And finally, the Waterford report, which is, I think, several hundred pages report, very comprehensive, can be accessed from this the last link shown here. If you have any questions, please email me, and I will also forward that email to my team. Thank you.
Okay, thank you. Thank you, Zong-Liang. In the interest of time, we have to move on to the next presenter, but if there's anybody got any questions, please write them in the chat so that Zong-Liang can answer them in the chat. I'm going to just stop sharing now. I'll just ask, actually I have a question here for Zong-Liang while we're waiting for Jamal. So we experience of working with Austin Water. I just wonder whether you'd shared that with other cities or which are affected by drought in southern US, like the experience of it, and maybe it's whether other cities have been interested in the work that you've done, whether they want to try the same method to like be able to plan for infrastructure in future.
Yeah, after that project's completed, we've been working with TWDB, which is State Agency, Texas Water Development Board, to develop naturalized stream flow for the future for other river basins in the state of Texas, like Nueces River and in the southwest of the state. And when carrying out this project, we also have a task technical team, like experts from other cities, like Denver or Pacific Northwest area. They serve scientists from those regions, cities. They serve as experts in the technical advisory capacity. So they know our progress, and they consider this is one of the examples they could also apply to other regions who have similar problems, similar droughts, flooding issues.
Okay, thank you.